In this video, we're going to spend some more time looking at differentiating trig functions. We've already seen the chain rule, the product rule, and the quotient rule. We're now going to look at a range of techniques we can use to differentiate trig functions. Later on in the video, we're going to look at a range of proofs, but for now, we're just going to build on our standard results. So if we go to our table of standard results, we saw that if we had now y is equal to sine x, the derivative dy by dx was cos x. So standard result y was sine x, the derivative dy by dx is cos x. If we had cos x, the derivative of cos x was minus sine x. If we had tan x, the derivative of tan x was sec squared x. If we had sec x, the derivative of sec x with respect to x was sec x tan x. If we had cosec x, the derivative of cosec x was minus cosec x cot x. And then finally, if we had cot x, the derivative was minus cosec squared x. We're going to look at some work with these particular functions and later on go on and derive now these last four using either the chain or the quotient rule. So let's start off with some basic examples and we'll work with some functions of functions. We've already looked at functions of functions and using the chain rule. We've used either a u substitution or we've done this simply by writing out now the derivative of the outside function, then we've rewritten the inside function and then we multiply through by the derivative of the inside function. Initially I'm going to work with a more formal approach by using the u substitution, and then we will look at some other examples just going through with the informal approach. So let's start off. Let's say we had now y is equal to the sine of 3x plus 1. So sometimes we'll be asked now to simply find the derivative of a function such as sine of 3x plus 1. So what we have here are two functions. We have sine x and we have 3x plus 1. We could say now by the chain rule, let u be equal to the inside function, which is 3x plus 1. Therefore, we have y is equal to sine u. By the chain rule, we can say that dy by dx will be equal to dy by du multiplied by du dx. So, if we've got now y is equal to sine u, we can say that dy by du is going to be cos u, and we're going to multiply that by du dx. So if I'm differentiating u with respect to x, we simply have 3. The derivative of 3x plus 1 is 3. So we can say now that dy by dx in terms of u will be now 3 cos u. We know though, and we can say, but u is equal to 3x plus 1. So we end up now with the derivative dy by dx will be 3 cos of 3x plus 1. So that's the formal approach. The way we often do this is simply to say differentiate the outside function, rewrite the inside function and multiply through by the derivative of the inside function. So for example now if we had y is equal to 4 sine of 5x plus 2, we would differentiate the outside function. So we could write now dy by dx, and this is the informal approach, would be 4 cos now of the inside function which we rewrite, and then we multiply through by the derivative of the inside function. The derivative of 5x plus 2 is simply 5. So we could write now that dy by dx will be equal to 20 cos of 5x plus 2, and that's the informal approach. So we differentiate the outside function, so sine x becomes cos x, we rewrite the inside function and multiply through by the derivative of the inside function. Let's go ahead and take another function. So let's say we've got now y is equal to 2 cos, and then we take now 5x cubed, and then we have plus x squared plus 4. So what we want is the derivative. So we've got a function here of a function. This is the inside function, 5x cubed plus x squared plus 4, and then this is the outside function. So with the formal approach, we could say now let u, and we'll write this here, let u be equal to the inside function, which is 5x cubed plus 4 plus x squared, and let's write that in, plus 4. So plus x squared plus 4. So just jotting this down, x cubed plus x squared plus 4. So what we now have is y is equal to 2 cos u. So if we want now dy by du, we differentiate y with respect to u, and that will give me minus 2 sine u. The derivative of cos u is minus sine u. If we have now du by dx, I'm differentiating now u with respect to x. So multiply down by the power and drop the power by 1. Multiply down by the power and drop the power by 1. And differentiating a constant gives us 0. So we can now say that dy by dx by the chain rule is dy by du multiplied by du dx. So we're going to get minus 2 sine u. And then we will multiply this by the 15x squared plus 2x. Now we know that u is this function right here, so we can rewrite this. So we can say that dy by dx will be equal to minus 2, the sine now of the 5x cubed, then we got plus x squared plus 4 multiplied now by the 15x squared plus 2x. So let's just write this here. And we just have to be a little careful. Let's just bracket that off. And then we're going to have now 15. And I can write this taking the common factor of x out. We'd have 15x plus 2. So we could tidy this up and we could say now that dy by dx would be equal to minus 2x multiplied by 15x plus 2 multiplied now by the sine of the quantity 5x cubed plus x squared plus 4. That's the formal approach. I personally would like to differentiate the outside function. So if we did that, we'd have minus 2 sine now of the inside function, which is 5x cubed plus x squared plus 4, and multiply through by the derivative of the inside function. So the derivative now of the inside function, if we got 5x cubed plus x squared plus 4, is 15x squared plus 2x. And then we could tidy up in the same way. Differentiate the outside function, rewrite the inside function, and multiply through by the derivative of the inside function. So if we're dealing with functions of functions, in general we can say now that if y is equal to the sine of f of x, so what we're looking at here now is the sine of now, so this is a function of a function. So all we would end up now with, the derivative dy by dx would be equal to f dashed of x multiplied now by cos of now the f of x. So all we're doing is simply multiplying through by the derivative once we've differentiated the outside function. So that would be our derivative. If we had now y is equal to cos of some function of x, so we have a function of a function, we can say now that the derivative dy by dx would be now minus, because we're going to end up now with a negative sign. So we've got minus f dashed of x multiplied by the sine now of the f of x. That's a little formal for my liking. All we're doing is essentially using the chain rule. So there's a brief intro looking at now at differentiating functions of functions. Let's move on and look at something slightly different. One of the results of the chain rule is that if we have now dy by dx, that will be equal to 1 over dx dy. We might be given now some particular derivative to find when we've got now x in terms of y. So usually we're dealing with the f of x now, so y is equal to the f of x. We might have it the other way around. We might have x in terms of y. So we might be asked to now find, so let's write this here, we might be asked to find dy by dx now 4, and we could have x is equal to 3 sine of 4y. And we might be asked for this in terms of x or in terms of y. Let's start off now with this in terms of y. So what I'm going to do here is differentiate. So I'm going to differentiate both sides of this equation with respect to y. We usually differentiate with respect to x, but in this particular case, I'm going to write dx dy. Now I need to differentiate 3 sine 4y with respect to y. So doing this informally, we're going to now have 3 cos of 4y. So I'm differentiating the outside function, I'm rewriting the inside function, and I'm multiplying through by the derivative of the inside function. The derivative now of 4y with respect to y is 4. So we can see that dx dy will be equal now to 12 cos of 4y. So we want dy by dx. All we need to do is invert this. So we can write that dy by dx in terms of y will be 1 over 12 cos of 4y. Now at this stage, if we wanted, using our reciprocal trig identities, we could write that dy by dx will be equal to 1/12 sec 4y. We know that 1 over cos x is sec x, so if we have 1 over cos 4y, we could write this now as 1/12 sec 4y. That's writing it in terms of y. If we were asked to write it in terms of x, we can use trig identities. So if we pick it up just here, we can write this now in terms of x. So let's use one of our trig identities. We know cos squared theta plus sine squared theta will be given as 1. That is a trig identity. So if we look at this right here, we can say x over 3 all squared will be equal now to sine squared of 4y. So all I'm doing is dividing by 3 and squaring this. If we look at this just here, we've got 1 over 12 cos 4y. So using the identity here, what we can say now is that cos squared theta would be now 1 minus sine squared theta. So in this particular case, we can say that cos 4y will be now the square root of 1 minus x squared over 9. So if we just look at what I've done here, I've simply now used the trig identity. We know that sine squared 4y is equal to this quantity here. We know the trig identity cos squared theta plus sine squared theta is equal to 1. Cos squared theta is 1 minus sine squared theta. So taking the square root, I can write that cos 4y is 1 minus x squared over 9. And you might want to show a couple more steps in that, but essentially this is what we have. So at this stage, we could write now that cos, and just tidying this up slightly, cos 4y will be now, and just combining the fractions, the square root of 9 minus x squared all over 3. So all I've done is combine the fractions and taken the square root of 9. So at this stage right here, we can pick up dy by dx and simply sub in. So we can say dy by dx in terms of x is going to give me now the following. I've got here 1 over 12 lots of the square root of 9 minus x squared over 3. We can see the 12 and 3 are going to cancel, so we can say that dy by dx in terms of x will be 1 over 4 lots of the square root of 9 minus x squared. So all I've done is use trig identities now to express dy by dx in terms of x. I first did it in terms of y by differentiating both sides of the equation with respect to y, and then I went ahead and used trig identities. Cos squared theta plus sine squared theta is 1, therefore x over 3 all squared is sine squared 4y. So cos 4y will be the square root of 1 minus this value. We can do a bit of rearranging, sub in, and now we can put our derivative dy by dx in terms of x. Okay, let's move on. Sometimes we'll need to differentiate powers of sines and cosines, and we can do this using the chain rule. So let's go ahead and look at a nice basic example. Say we've got y is equal to sine squared x, and we want to find the derivative. We can write this as y is equal to the sine of x squared. So these two things are identical. At this stage, we can use the chain rule. So if we look at this particular case, our inside function is sine x, our outside function is x squared. So using the chain rule, we can say that dy by dx, we differentiate the outside function, which is going to give me 2. So I've multiplied down by the power. I rewrite the inside function. I drop the power by 1 and multiply through by the derivative of the inside function, which will give me cos x. So we can say that the derivative dy by dx is going to be 2 sine x cos x. Now, often on an exam question, they might ask you to show that the derivative of sine squared x is sine 2x. Now, we know the identity that 2 sine x cos x is now sine 2x, so we can write that dy by dx is sine 2x. So that's one way that we could do this. We might be asked for something else. We might, for example, let's take another function. Let's say we've got y is equal to 4 lots. Now, and let's take something slightly more challenging. Let's say we've got now cos of, let's go for 5x. Cos of 5x, which we will cube. So we've got 4 cos cubed of 5x. So we can write this now as 4 cos of now 5x, which we're going to now cube. So all I'm doing is taking the power here. So we can see we've got a function of a function of a function. We've got now 5x, we've got cos x, and then we've got x cubed. So what we need to do is differentiate the outside function. So if I differentiate the outside function, taking it now to be x cubed, we're going to multiply down by the power. So I'm going to multiply down, we're going to have 12, then we'll have rewriting the inside function cos of 5x. We drop the power by 1 and multiply through by the derivative of the inside function. So again, we're using the chain rule on that inside function, and the derivative now will be minus 5 sine of 5x. So what we end up with then is now dy, and let's write this here, dy by dx rather than just y, dy by dx by now the chain rule, we've got minus 60, and then we've got sine of 5x multiplied by cos squared of 5x. Now, as you can see, that's pretty involved. We've taken a function of a function of a function, so function of function of a function, and we simply now used the chain rule. So let's look at another example. Let's say we've got y is equal to now, let's say we've got cos to the 4th of x. So we've right now y is equal to cos x to the power of 4. We would differentiate the outside function. The outside function here is going to be x to the 4th. So dy by dx will be equal to multiplying down by the power, rewriting the inside function, dropping the power by 1, and multiplying through by the derivative of the inside function. So we end up now with the derivative dy by dx as minus 4 sine x cos cubed x. And that is simply now an application of a chain rule. So sometimes we're going to look at powers of sines and cosines, and it's simply going back to this idea of having a function of a function and applying the chain rule. Sometimes we might need to differentiate what look to be products or quotients. Often we can do these using trig identities to simplify first. So let's look at an example of this. We might now have, for example, y is equal to, let's go for y is equal to now, let's go for 4 sine of now 2x cos 2x. Now at the moment this looks like a product. So it looks like we've got two functions of x multiplied by one another. And we've seen if we've got a product, we would use a product rule, and we'd have two functions of x. It would be u and v. And the derivative would be v du dx plus u dv dx, as we've seen in previous videos. Let's just look at this though and see what we could do. Now we know that the sine of 2x will be equal to 2 sine x cos x. So if we look at what we've got here, we've got 4 sine of 2x cos of 2x. So in this particular case, what we could say is that this right here could be written now as y is equal to 2 sine of 4x. So 4 sine 2x cos 2x is actually 2 sine of 4x. At this stage now, the derivative is fairly straightforward. So all we would do now is differentiate. So we would see now that this would become 2 cos of 4x. So we're differentiating the outside function, rewriting the inside function, and multiplying through by the derivative of the inside function. So dy by dx will be equal to 8 cos of 4x. And that now gives us our derivative. So with this particular case now, it's simply a case of looking and saying, can I write that now using a trig identity? Do I need now to go through the rigmarole of using the product or the quotient rule to deal with these kind of problems? Obviously, there will be times when you need to use the product or the quotient rule when you are dealing with trig functions. An example might be if y, let's do one here, if y is equal to x cos x. So here we've got a product. So we've got x, which is an algebraic function, multiplied now by our trig function. So all we would do here is use the product rule. And we've seen the product rule in action time and time again. We would let u be equal now to x. The derivative, as we saw in the video, du dx would be 1. We would take v to be cos x, and the derivative dv by dx would be minus sine x. So if we've got now a product, the product rule says if y is equal to u multiplied by v, where u and v are both functions of x, then dy by dx would be equal to v du dx plus now u dv dx. So all we're doing, as we saw in the video, is multiplying these two and adding it to the multiple of those two. So we could say now that dy by dx would be equal now to cos x times by 1, so one lot now of cos x, and then we would add to that now the x multiplied by minus sine x. So we could go ahead and tidy this up and say that dy by dx was equal to cos x minus x sine x, and that's just using the product rule. Later on in the video, we're going to look at the proof of the derivative of sine x being equal to cos x and the derivative of cos x being equal to sine minus sine x. Now, you won't be expected to reproduce those proofs, but you will be expected to derive particular results using now sines and cosines and the rules that we've learned. So let's go ahead. Now, we know that the derivative, so the derivative with respect to x of tan x is equal to sec squared x. And you might be asked to show this or derive this in an exam question. And the way we can do this is to use the quotient rule. We can write now that y is equal to tan x, which is the sine of x, over the cosine of x. So here we can see that we've got a quotient. So let's go ahead and use the quotient rule. So we've got u over v. U and v are both functions of x. So we let u be equal to the sine of x. We let now, or we say that du dx, the derivative will be cos x. If we now take v is cos x, the derivative with respect to x, which is dv by dx, is going to be minus sine x. So if y is equal to u divided by v, where u and v are both functions of x, by the quotient rule, dy by dx will be v du dx minus u dv dx all over v squared. If you do need to review that, there is quite a lengthy tutorial on the quotient rule. So let's go ahead and do that. Let's write this in. So dy by dx, we're going to now have the following. So let's just set this equal. We're going to have these two multiplied, which is going to give me now cos x multiplied by cos x, which is cos squared x. We now square these two and subtract it away, which will give me minus sine squared x, and we put it all over v squared, which will be cos squared x. So we have now that dy by dx will be equal to cos squared x plus sine squared x over cos squared x. At this stage, we know the trig identity that cos squared x, or cos squared theta plus sine squared theta, is equal to 1. We can say cos squared x plus sine squared x is equal to 1. Therefore, now we've got that dy, I'm writing here, therefore dy by dx will be equal to 1 over cos squared x, and we can say that dy by dx, using our reciprocal trig identities, 1 over cos squared x is equal now to sec squared x. And you might just want to put a note that 1 over cos squared x is sec squared x. So all we've done is use the quotient rule to show one of our standard results. The standard result now is the derivative of tan x with respect to x is sec squared x. Let's now look at sec x. So if we now want the derivative, so let's say the derivative with respect to x of sec x, this gives us now sec x tan x, and this is one of the results that we've been quoting throughout the videos. So let's go ahead and look at this one. What we could say now is the following: let y be equal to, this is 1 over cos x, or we could write this as cos x to the power of minus 1. Now this isn't cos to the minus 1 of x, it's not the inverse function, it's the reciprocal trig identity. At this stage we're going to use the chain rule. So dy by dx, we multiply down by the power, we rewrite the inside function, we drop the power by 1, and we multiply through by the derivative of the inside function, which is going to be minus sine x. So the minuses cancel out, and we've got now that dy by dx is equal to, in the numerator, sine x, in the denominator, cos squared x, or I'm going to write now cos x, cos x. And the reason I'm going to do that now is we can see that this fraction can be split up. So what we've got then is dy by dx is equal to 1 over cos x multiplied by sine x over cos x. We know that 1 over cos x is sec x. We know sine x over cos x is tan x. So we can say that dy by dx is sec x tan x. And again, you might want to just put to the examiner that the identities 1 over cos x is sec x, sine x over cos x is tan x. So all we've done is simply now applied the chain rule. Let's go ahead and do another one. Let's look at the derivative of cosec x. So the derivative of cosec x with respect to x. This gave us now minus, so let's write this here, derivative of cosec x is minus cosec x cot x. So let's look at this then. So let y be equal to cosec x, which is 1 over sine x, or sine x to the power of minus 1. Application of the chain rule again, and again you might want to put this down that you're using the chain rule. We can say that dy by dx will multiply down by the power, we'll rewrite the inside function, we will drop the power by 1 and multiply through by the derivative of the inside function. The derivative of sine x, as we now know, is cos x. So we end up now with dy by dx will be equal to minus cos x over now sine squared x, which is sine x multiplied by sine x. And again, I'm just going to write this as 1 multiplied by that value. So we can split this fraction up. So we've got dy by dx will be now 1 over sine x, and we'll put the negative there, multiplied by cos x over sine x. This gives us cosec x, this gives us cot x, therefore we show the result. And if you just want to write now 1 over sine x is cosec x, cosine x over sine x is cot x. And that is shown now that the derivative of cosec x is minus cosec x cot x. Okay, that just leaves us now with cot x, so let's do the derivative. So the derivative with respect to x of cot x is now minus cosec squared x. And this goes back to now when we looked at the derivative of tan x. We simply use the quotient rule and rewrite this. So we say let y be equal to cot x. Cot x is cos x over sine x, as we've seen before. So we got quotient here, and let's go ahead and do that. So let's just use the quotient rule. Let's put this up now. So we've got the following. We've got now u, that's going to be cos x. We've got now the derivative du dx, and that's going to be minus sine x. We've got v in the denominator, which is going to be sine x, and the derivative dv by dx is going to be cos x. So we can see at this stage dy by dx, and this again is going to be using the quotient rule. We multiply these two, which is going to give me minus sine squared x. we subtract away the multiple of these two, which is minus cos squared x, and we put all of this now over v squared, which is sine squared x. It looks a bit messy as it is, but we can go ahead and factor that numerator. So dy by dx will be minus the quantity sine squared x plus cos squared x. So all I'm doing there is just taking now the negative out and putting that over sine squared x. We know that sine squared x plus cos squared x is equal to 1. Therefore, now the derivative dy by dx will be equal to minus 1 over sine squared x. 1 over sine squared x, and we can write this here, therefore dy by dx will be equal to minus cosec squared x. And a little note to the examiner that 1 over sine x is equal to cosec x just shows now that we've derived that derivative. So dx of cot x is minus cosec squared x, simply by using the quotient rule. Let's now move on to looking at a range of derivatives. So what we're going to do is look at sine x, cosine x, cot x, tan x, sec x and cosec x, and look at particular functions of functions. So let's say we were asked to differentiate y is equal to tan of 4x. So we have a function of a function. The outside function is tan x, the inside function is 4x. We could use the chain rule formally. We could let u be equal to 2x. Therefore, 4x, let's put 4x, y is equal to tan u. dy by du would be equal to the derivative of tan with respect to u. So tan u with respect to u, which will be now sec squared u. If we look at du dx, du dx is simply going to be the derivative of 4x, which is 4. So we can say that dy by dx would be 4 sec squared u. This is simply using the chain rule. We know that dy by dx will be equal to dy by du multiplied by du dx. So I can see here now, in terms of u, it's going to be sec squared u multiplied by 4. So we could write dy by dx would be 4 sec squared 4x. And that now is the derivative of tan 4x. Again, you might want to do this mentally or just do it on paper and just write now that if y is equal to tan of 4x, we differentiate the outside function. So dy by dx is going to be sec squared. We rewrite the inside function and then we multiply through by the derivative of the inside function. And you can see that's going to give me exactly the same right there. So differentiate the outside function, we rewrite the inside function and multiply through by the derivative of the inside function. So let's go ahead and look at another example. Let's say we have to differentiate. Let's have y is equal to minus 2 and then we'll have sec of 3x. So let's just think about the derivative of sec x. The derivative of sec x is sec x tan x. So what we could do now here is write that dy by dx will be equal to minus 2. Then we'll have sec of 3x, tan of 3x, and then we'll multiply through by the derivative of the inside function, which will be 3. So we can write that dy by dx now, by the chain rule, was minus 6 sec 3x multiplied by tan 3x. So I've differentiated the outside function. The derivative of sec x is sec x tan x. I've then multiplied through by the derivative of the inside function. The inside function was 3x. We've rewritten that inside function and simply gone ahead and dealt with it. Okay, let's look at another one. Let's look at something else. Let's go for y is equal to sec 2x divided now by cosec 2x. So in this particular case, again, it looks like we've got a quotient to deal with. But let's go ahead and use some trig identities. So we could say now that y is equal to 1 over cos 2x over now 1 over sine, let's write this in, 1 over, and just scribble that out, 1 over sine 2x. So all I'm doing is using the reciprocal trig identities. So we could actually say now that this is y is equal to tan of 2x. So if we consider, all we're doing now is simply inverting the fractions and multiplying. So 1 over cos 2x divided by 1 over sine 2x is going to give us now tan of 2x. So what do we need? We need to differentiate tan 2x. So we differentiate the outside function, which will give us now sec squared. We rewrite the inside function, which is 2x, and multiply through by the derivative of the inside function, which will give me 2 sec squared 2x. So dy by dx will be 2 sec squared 2x. So using a trig identity, we've gone ahead and dealt with that particular derivative. Let's try something slightly more challenging. Let's say we've got y is equal to the square root of 3 minus sine squared x. So just rewriting, y is equal to 3 minus sine squared x to the power of 1/2. So again, this is just an application of the chain rule. So we'll have now dy by dx. We will differentiate the outside function. The outside function is now the square root of x, or x to the 1/2. So differentiating, we multiply down by the power. We rewrite the inside function. We drop the power by 1, which will give me minus 1/2. And we multiply through by the derivative of the inside function. Now we're differentiating minus sine squared x. That will now give us minus 2 sine x cos x, as we've seen before. Just consider what I'm differentiating. I'm differentiating now minus sine x squared. So if I differentiate this, I multiply down by the power, I rewrite the inside function, I drop the power by 1 and multiply through by the derivative of the inside function. And that is to the power of 1 rather than minus 2 sine x factorial. Hopefully you can see that's the case. So we could write now that dy by dx would be equal to, the 2 and the half are going to cancel, minus sine x cos x, now over the square root of 3 minus sine squared x. Or you could just say that's minus 1/2 sine to x. And many of these questions will get you to think of different ways of looking at these. So that's quite a nice example and something slightly more involved. So you're looking at multiple functions here, and it's just a case of keeping on top of your work. In later videos, we'll look at a range of exam style questions. So when the exam style questions come in, we will be looking now at tangents, normals, stationary points, and so on and so forth. But hopefully that's given you a good insight into differentiating trig functions. The vast majority of these can be done using standard results, so the standard results we know, and also applications of the chain rule. What we're now going to do is go on and look at the proof of the derivative of sine x being equal to cos x and the derivative of cos x being equal to minus sine x. Now this is very much a bolt-on to what we're doing. You don't need to know it for this particular course, but I think it's interesting all the same. So let's go ahead and look at this. What we want to show then is that the derivative, so the derivative with respect to x of sine x is equal to cos x. And we're going to do this from first principles. Some of this you just either have to understand or accept or just appreciate that it's a result of some trig identity or a limit. Differentiation by first principles says now that the derivative f dashed of x will be equal now as the limit, so we have a limit as the value of h tends to 0 of now the f of x plus h minus the f of x all over h. And this now gives us where we start from in terms of differentiation from first principles. And we've seen this before many times lower down the course. So when we're looking at the limit now as h, this small quantity that we're increasing the x coordinate by, and then we're simply watching that tend to 0, and we end up now with the f of x plus h minus the f of x all over h. So let's go ahead and apply this to sine x. So what we can say then is the derivative, and I'll write it here, d dx of sine x is going to be now the limit as h tends to 0 of the sine of x plus h minus the sine of x all over h. At this stage, we use one of our trig identities, and we also use a small angle approximation. If we just go back to one of our trig identities, we know that the sine of p minus the sine of q is equal to 2 now cos of p plus q over 2 multiplied by the sine of p minus q over 2. And this is quoted in the formula book. So what I'm going to do is just work with this. If we consider just here, what we've got is p. P is the quantity here. So if I write this out, what I can say now, just jotting it down, p will be equal to x plus h. And this is one of the many ways of showing this particular proof. It's certainly not the only way. I can think of 2 or 3 other ways that you might be showing this. So what I've done, I've taken sine of p, I've let p be equal to now x plus h, minus sine of q. So now we can say that q is going to simply be now the quantity on here, x. So all we're doing now is saying that we're going to end up with q being equal to x. What I'm going to do is rewrite this. We can see that this can be written in the form 2 cos of p plus q over 2. So if we look now at p plus q over 2, I'm going to add these two values together, which is going to give me 2x plus h over 2. If I look at p minus q over 2, that's going to give me now, subtracting these two, we're just going to have h over 2. So what we can say now is the derivative with respect to x as sine x as the limit of h, this small value that we're increasing the x-coordinate by, tends to 0, and let's just put that in, as h tends to 0, will be the following. We're going to have 2, and then subbing these values in, we're going to have 2 lots of a cos, and I'm going to write this now as x. I've got 2x over 2, which is going to give me x, plus now h over 2. Then I'm going to have the sine of h over 2. And this is all over h. At this stage, I'm just going to divide through by the 2. So we've got the derivative with respect to x of sine x as the limit now of h tends to 0. This is going to be cos now of x plus h over 2 multiplied now by the sine of h over 2 all over now h over 2. So I've simply divided through the fraction. This is where we apply now another result, and this is a result for small angles. If we consider the sine curve, and this is something that we need to either know, understand, or simply rely on. If we have now sine of h, and we have the line h, let's just put this here, and I'll do this in terms of theta to begin with. We can say for small values of theta, we can say sine theta will be equal to theta as, and just write it here, as now theta is small or tends to 0. Therefore, what we can say at this stage right here is if we have the sine of theta over theta, that's going to be equal to 1. Now let's look at that here. What I've got here is the sine of h over 2 over h over 2. So we can say now that the sine of h over 2 over now h over 2 as now h, or h over 2 tends to 0, will give us 1. So at this stage we can simply sub that in. So we can say now the derivative with respect to x of sine x as the limit of h tends to 0 is going to give us now, let's put this in, tends to 0, is going to be cos, and we'll write it in, we're going to have now cos x. Now just consider what's going to happen here. H over 2 is going to tend to 0, and I'll just write it in like so. Let's just put this here, and then what we're going to have here is this part is going to give us 1. So we can now write, let's put it in, we're going to say now that the derivative d dx of sine x is going to simply give us now, remember this is tending to 0, that will now give us cos x. And that's one way of showing it. So we end up now with simply the limit tending to 0, this is going to give us cos x. we've seen that sine of h over 2 tends to now 1 as h over 2 tends to 0. And that's for proof. As you can see, it's fairly involved, and you certainly wouldn't be expected to show it. But hopefully that gives you some idea of one way of showing it. So what we've done is use the standard result of differentiation from first principles. We've used this identity that sine of p minus sine of q is 2 cos of p plus q over 2, sine of p minus q over 2. We sub that in, and we simply now looked at what happens. As h gets very small, we end up now with sine of h over 2, which is 1, and this now will give us the derivative with respect to x as sine x being equal to cos x. In terms of now a proof for cos x, the derivative, and let's just write here, if we say now the derivative with respect to x of cos x, we know from our standard results that this is minus sine x. And there are similar ways to showing this using either double angle or these particular identities. But at this stage, we can simply use the chain rule again. So as you can see, the chain rule is quite well used. So let's write cos x. Now from trig identities, we can say that cos x is the sine of pi by 2 minus x. So what we're looking at then is the derivative of, and we'll write it just here, we'll have now the sine of, and writing it in, we're going to have pi by 2 minus x. So what I want to do now is show that this is going to be equal to minus sine x. If we consider this now, let's just put this here. We want to show that that's minus sine x. So let's go ahead and differentiate this. So let y be equal to the sine of pi by 2 minus x. So by the chain rule, dy by dx, we'll differentiate the outside function. So differentiating sine, we're going to get cos. We rewrite the inside function, which is going to give me now pi by 2 minus x, and multiply through by the derivative of the inside function. And the derivative now of minus, or pi by 2 minus x is just minus 1. So we get that dy by dx, or the derivative with respect to x of cos x, is minus cos now of pi by 2 minus x. Now cos of pi by 2 minus x is sine x, but we might want to show this using the addition formulae. I doubt that you would be expected to show it, but it's worth it anyway. So what we're going to get then is, if we use the addition formulae, we get the cos of pi by 2 multiplied by cos x plus now sine of pi by 2 multiplied by sine x. And this is just, again, using the addition formula. So dy by dx, using the chain rule, is going to be minus this. Cos of pi by 2 is 0, so we're going to have 0. And then sine of pi by 2 is 1, we're going to have sine x. So we can see that dy by dx is simply now minus sine x. And that is one way of showing it. So those two ways that I've shown it now, in terms of the trig identities and the fact that now sine of theta is equal to theta for small values of theta, is one way. In books, in tutorials, in lectures, you might see it being done other ways, and I think there are alternatives that you might want to use. And then all we've done is simply now applied the chain rule to show that the derivative with respect to x of cos x is minus sine x by using trig identities and going through there. This, you could argue, is not necessary, because we can simply state that the derivative now, and this gives us cos of pi by 2 minus x, this is just sine x. That's just something that we hopefully should be cool with if we just draw this up. So let's say now let's draw this triangle. Let's just have a 3, 4, 5 triangle. So if this now is 5, this one is 3, this one is 4, this one is x, and this now is pi by 2 minus x. If we consider now cos of x, so cos of x is going to be equal now to 3 over 5. That is the adjacent over the hypotenuse, and then the sine of x minus pi by 2 is the opposite over the hypotenuse. That is 3/5, and we can see therefore these two are equal. And we could quote that just here, and vice versa, and you can see exactly the same. Entirely up to you on how you wanted to view that. Or you could show it graphically. So there we go, that's now proof of sine x and cosine x for derivatives. You won't need to show that. You will need to derive those ones earlier, the tan, the sec, the cosec and the cot, but that is just an extension. So there we go. In the next couple of videos we will look at some exam style questions on differentiating trig functions.